Alright, we should be live any moment now. I'm waiting for it to show that I am. Shout out, what is it, UK drill instrumentals on Spotify. This is what we're gonna be listening to for the duration of this live, of this stream. Okay, here we go. Check, check. How's the sound quality? I gotta see on that playback. Yeah, it's not too bad. I guess we'll continue moving forward with it. Alright, I'm gonna turn this back on.
What made this one?
Okay, the desktop audio could be a little bit louder. That's better. I'm gonna go a little bit louder. Let's see. Maybe that's too loud. A little bit louder. Let's see. Nah, that should be good. Here, let me do some yapping with the music already going. Alright, so today I'm going to be continuing my studies of chapter 29. Alright, we're gonna have some clash there, but whatever, let's continue rolling. Wait, well, wait, actually I do want to make certain that it is good. So let me cut this now. Chapter 29. Alright, we're gonna have some clash there, but whatever, let's continue rolling. Wait, well, wait, actually I do want to make certain that it is good. Alright, that's pretty good. I'm gonna turn it down just a hair, and then that's perfect. Alright, let's continue now. Hey. Okay, whoa. Let's see. So today, during this stream, I'm going to continue my studies of chapter 29, Electromagnetic Induction, in the book University Physics, Volume 2, 14th edition by Young and Friedman. This is what I'm progressing in today. And we're just talking about electromagnetic induction. Which is looking at the induction of the induction of a magnetic field or an electric field because of the presence of another exterior magnetic field. And particular to this case, an exterior magnetic field is what we'll be looking at. Most commonly uniform magnetic fields, so things won't get incredibly complex, but it will be interesting. So I'm still waiting for it here. Maybe it's just not rendering to see that I'm live on X. Okay, it does say that I'm live. Alright, fantastic. So I'm live there. Whoops, I had myself coming through the speaker or something, I believe. Yeah. Let me turn this off. Okay. Yo! Alright. And I'm also live on YouTube for the first time. Oh my goodness, now. What's up with this quality? Okay, there. Now we got 720 pixels. I don't want to hear it though. Shut up. Okay, we're good there. Why? Here it shows that I'm live, I guess, whatever. Okay, let's go back to YouTube. I want to make sure that that's working properly. Oh man. Okay, phone, no cooperation or what? Alright, fantastic, here we are. Everything seems to be in order, in line, so... And what, did I start recording this as well? Yes, I did. Alright, because I'm going to be uploading this to Rumble and then to YouTube as well, so you can go and check out the videos there if you're interested. Alright, so let me start by saying hello, welcome to the stream. Again, we're going to be continuing our studies in electromagnetic induction. In particular, we're studying the book University Physics by Young and Friedman. It's volume 2, and we're on chapter 29. So, where I left off last time is generators as energy converters. So let's continue here. Example 29.6 shows that the side where a generator doesn't produce electrical energy out of nowhere. The energy is supplied by whatever body exerts a force that keeps the rod moving. All that the generator does is convert that energy into a different form. The equality between the rate at which mechanical energy is supplied to a generator and the rate at which electrical energy is generated holds for all types of generators, including the alternator described in example 29.3. We are ignoring the effects of friction in the bearings of an alternator between the rod and the U-shaped conductor of a slide wire generator. The energy lost to friction is not available for conversion to electrical energy, so in real generators the friction is kept to a minimum. In chapter 27, we stated that the magnetic force on moving charges can never do work. Oh yeah, so this is a very important point, so listen to this with intent. In chapter 27, we stated that the magnetic force on moving charges can never do work. The magnetic force on moving charges can never do work. You might think, however, that the magnetic force equals the current multiplied by the length crossed into the magnetic field, which is going to look something like this. Here, let me just draw the equation for you so it makes more sense. Okay, so... this is... Okay. Force vector equals the current multiplied by this length vector crossed into the magnetic field. Okay, so now that's the force equation. Okay. The magnetic force of moving charges can never do work. You might think, however, that the magnetic force is doing negative work on the current carrying rod as it moves, contradicting our earlier statement. In fact, the work done by the magnetic force is zero. The moving charges that make up the current in the rod have a vertical component of velocity, causing a horizontal component of force on these charges. As a result, there is a horizontal displacement of charge within the rod, the left side acquiring a net positive charge and the right side a net negative charge. The result is a horizontal component of electric field, perpendicular to the length of the rod, analogous to the Hall effect described in section 27.9. It is this field in the direction of motion of the rod that does work on the mobile charges in the rod and hence indirectly on the atoms making up the rod. Okay, so what is being said here is that the magnetic force is not what does work on the charges, but it is the magnetic force which causes a separation of charges. You get a positive and negative separation of charges, analogous to the Hall effect, which you could look that up, the Hall effect, and it'll kind of give you an idea of, or a representation of what this looks like. Here, let me look it up here. So a magnetic field does not do work on charged particles, but a magnetic field itself causes this causes a polarity shift in where you have a separation of negative and positive charges. And upon the magnetic field causing this separation of charges, you get inherently an electric field. And this electric field is what is going to do work through the electric force, do work on the particles, or on the charged particles. So how intriguing, right? Because previously I would have thought, you know, the work is being done by the magnetic field, although it's untrue. It's untrue. So here, maybe something like this, you know. You present a magnetic field to a conductor, and then the free electrons are going to be divided to the one side, meaning that there's holes or lack of electrons on the other side, causing a positive charge. And this is what's going to happen in the material because of the poles of the magnet. Right. And this is further discussed in previous chapters, which I've already gone over, but I haven't done any videos on, so this is where we're going to continue forward from. Though I'm thinking that maybe I could do a streaming series on just the whole book itself, which is this volume 2, and volume 1 covers more classical mechanics, such as like the beginning of kinematics and things like this. I mean, looking at vectors, in which I can explain all of this to you through through a chapter on gravity. You know, we have fluid mechanics, trying to think, obviously we have what else? Oh yeah, circular motion, you know, a whole chapter on that, projectile motion, you know, that's thrown in with the kinematics and things like this. But anyways, you know, there's much that could be covered that I have not covered yet. And so there's a lot of opportunity for content. I suppose we'll see where things take us, but I think that's a route that I'll be going. But yes, let's continue. We're chilling now. Okay, again, this is our, that's the equation that we're looking at currently. So how interesting that the magnetic force can never do work on moving charges, but rather it is this the polarity that's caused, or separation of charges that's caused by the presence of the magnetic field. And this separation of charges inherently creates an electric field, which is what's going to be doing work in application to this problem, because this problem obviously has some specific parameters that I haven't actually discussed yet. But whatever, it's just the concept that, that the magnetic force on moving charges can never do work. Okay, let's keep that in mind. Alright, so chapter 29, section 3, 29.3, Lenz's law. Lenz's law. And I've heard of this law, and what are they? Lenz. let's continue. 29.3. Alright, let me give you some visuals, something nice to look at. I'll write it down here. This is how you spell it. I would leave that there for now, right? Look for you. Lenz's law. Okay, Lenz's law is a convenient alternative method for determining the direction of an induced current or EMF. Lenz's law, named for the Russian physicist H.F.E. Lenz, 1804 to 1865, is not an independent principle. It can be derived from Faraday's law. It always gives the same results as the sign rules we introduced in connection with Faraday's law, but it is often easier to use. Lenz's law also, let's reread that. It always gives the same results as the sign rules we introduced in connection with Faraday's law, but it's often easier to use. Lenz's law also helps us gain intuitive understanding of various induction effects and of the role of energy conservation. Lenz's law states, the direction of any magnetic induction effect is such as to oppose the cause of the effect. Okay, I'm gonna write that down. Okay, the direction of any magnetic induction effect is such as to oppose the cause of the effect. Okay, so we'll write that down. Lenz's law. Shit. That's not up. The direction of any magnetic induction effect. The direction of any magnetic. Oh, what is that? Magnetic induction. Come on. Okay. Induction effect. Oh. Okay. Alright. is such as to oppose the cause of the effect. Induction effect is such as to oppose the cause of the effect. Come on, that was like ass. I really messed that up. The cause of the effect. Okay, and there it is. Okay. The direction of any magnetic induction effect is such as to oppose the cause of the effect. Beautiful. The cause may be changing flux through a stationary circuit due to a varying magnetic field. Changing flux is due to motion of the conductors that make up the circuit, or any combination. If the flux in a stationary circuit changes, as in example 29.1 and 29.2, the induced current sets up a magnetic field of its own. Within the area bounded by the circuit, this field is opposite to the original field if the original field is increasing but is in the same direction as the original field if the latter is decreasing. That is, the induced current opposes the change in flux through the circuit, not the flux itself. That is, the induced current opposes the change in flux through the circuit. Okay, so in a whole lot of mind fuckery, it's important to understand these sentences and have them as like a fundamental understanding of the physical behavior of a certain situation, because unless I understand this, I'm not gonna know how to set up my problem mathematically, which is gonna be much more difficult, no doubt about it. Okay, so with that being known, here, let's emphasize this. I'm gonna write this down in my notes. That the induced current opposes the change in flux through the circuit, not the flux itself. And let's reread the previous sentence to better understand that. Within the area bounded by the circuit, this field is opposite to the original field if the original field is increasing. So this field is opposite to the original field if the original field is increasing, but is in the same direction as the original field if the latter is decreasing. The cause may be changing flux through a stationary circuit due to a varying magnetic field. Changing flux due to motion of the conductors that make up the circuit, or any combination. If the flux in a stationary circuit changes, as in within the area bounded by the, as an example, the induced current sets up a magnetic field of its own. Within the area bounded by the circuit, this field is opposite to the original field. If the original field is increasing but is in the same direction as the original field, If the original field is increasing but is in the same direction as the original field, what the fuck? This field is opposite to the original field. If the original field is increasing but is in the same direction as the original field, if the latter is decreasing. The induced current opposes the change in flux. Okay, the induced current opposes the change in flux Okay. What's up, everybody? I hope you're having a great day. I hope things are going swell for you. I hope that you're working hard, and I hope that God blesses you. You know, at times life can be difficult, and we're not always certain of the direction that we're heading, but but we must keep our head high and our chin up and keep our eyes focused. Keep our eyes focused and our mind focused, for there are many things which are trying to drag us in all different directions, but we mustn't let us. Though we mustn't let it. Forgive me. I'm just double checking to make sure everything's running smoothly still on all the socials. Alright, fine. Okay. If the flux change is due to motion of the conductors, as in example 29.3 through 29.6, the direction of the induced current in the moving conductor is such that the direction of the magnetic field... Okay, whoa. If the flux change is due to motion of the conductors, the direction of the induced current in the moving conductor is such that the direction of the magnetic field force on the conductor is the opposite in direction to its motion. The direction of the induced current in the moving conductor is such that the direction of the magnetic field force on the conductor is opposite direction to its motion. Thus, the motion of the conductor, thus the motion of the conductor, which caused the induced current, is opposed. Thus, the motion of the conductor, which caused the induced current, is opposed. We saw this explicitly for the slide wire generator in example 2. In all these cases, the induced current tried to preserve the status quo by opposing motion or a change of flux. Preserve the status quo by opposing motion or a change of flux. Preserve the status quo by opposing motion or a change of flux. Lenz's law is also directly related to energy conservation. If the induced current in example 29.6 were in the direction opposite to that given by Lenz's law, the magnetic force on the rod would accelerate it to ever-increasing speed with no external energy source. Even though electrical energy is being dissipated in the circuit, this would be a clear violation of energy conservation doesn't happen in nature. If the induced current were in the direction opposite to that given by Lenz's law, the magnetic force on the rod would accelerate it to ever-increasing speed. Alright, so conceptual example. Lenz's law in the slide wire generator. The induced current in the loop causes an additional magnetic field in the area bounded by the loop. The direction of the induced current is counterclockwise. The direction of the induced current is counterclockwise. So from the discussion of section 28.5, this additional magnetic field is directed out of the plane of the figure. That direction is opposite that of the original magnetic field, so it tends to cancel the effect of that field. This is just what Lenz's law predicts. Lenz's law in the direction of induced current. There is a uniform magnetic field B through the coil. The magnitude of the field is increasing, so there is an induced EMF. Use Lenz's law to determine the direction of the resulting induced current. Alright, I don't know. Let's see how this goes. I'll do my best to draw something here. I'm not sure how it's going to look. Works. Okay. Okay, so this is what we have going on here. I got a loop of wire. Okay, something like that. Yikes, not going so well. But we managed to make it happen. Okay, so this is our loop of wire. Let's see. Okay, what's this say? There's a uniform magnetic field B through the coil. Uniform magnetic field B through the coil. Here, we're a little low here. Let me move this up. Okay, we'll come here. We'll leave Lenz's law in there so we know exactly what we're talking about here. Okay, so uniform magnetic field here. We'll draw this in red. Try to get a straight line. Okay, lag. Okay. I'm still not satisfied with the straightness of the line. Alright, something like this. So this is our uniform magnetic field. Gosh, where's my up and down? I don't know now. Up and down now, right and left. This thing's throwing all sorts of crazy angles at me. Oops. And now there's no going back to my arrow. Alright, fantastic. Now I just got rid of my loop. Cool. Trying to see if the lines on this thing are straight. The fuck? Alright, sorry, getting a little heated here now. Okay, yeah, that works out great. Thanks, bud. Okay, so uniform magnetic field here. It took us long enough to create this magnetic field, but finally it has been created. So we have a uniform magnetic field B through the coil. The magnitude of the field is increasing, so there's an induced EMF. It's increasing, and to show that this magnetic field is increasing, meaning the magnitude of it's getting bigger, you know, it's going from 0.5 Tesla to 1 Tesla. So to depict this, we're going to draw some dashed lines here to an arrow here because we have an increasing magnetic field. Okay, increasing magnetic field. Use Lenz's law to determine the direction of the resulting induced current. This situation is the same as in example 29.1. By Lenz's law, the induced current must produce a magnetic field be induced inside the coil that is downward. According to Lenz's law, the induced current from the magnetic field is going to produce its own magnetic field, which opposes this magnetic field here, so it's in an opposite direction. And so to depict this, I'm going to use a different color again. Okay, that's not what I want, you fucking asshole. I mean, I don't know, usually there's a color spectrum that pops up, but holy shit, not gonna happen for me. Alright, I don't know, let's denote it in orange. Ugly ass color. Let's do it. Okay, so this is the magnetic field that's essentially induced. Induced. It almost looks like and. Man, my drawings on paper are so nice, I swear. Working on this Intuos pad and it comes out looking like this. Okay, that's my vector, induced. Induced. Okay, so that's the induced magnetic field. Okay, this situation is the same, blah, blah, blah. Magnetic field inside the coil is downward, opposing the change in flux. Because we have an increasing flux in this direction. Okay, remember again that the induced current opposes the change in flux, but not the flux itself. So our change in flux is in this direction. Here, let's I don't know, maybe I can depict this in a particular way. Okay. So we'll do it in green. This is our change. Oh my gosh, I can't draw a straight line. This is our change in flux. Wow, this is crazy, man. Okay, boom, we got a change in flux in this direction, and so our induced magnetic field is going to oppose the change in flux. We have an increasing magnetic field here. Flux is in the positive direction. Our induced magnetic field is going to be opposite to that. Okay. From the right-hand rule we described in section 28.5 for the direction of the magnetic field produced by a circular loop, the induced current due to the change in B is clockwise as seen from above the loop. The induced current due to the change in B is clockwise as seen from the above loop. Okay. Right, and it's negative. Okay, so let me think. If we have an increasing magnetic flux, so to use the right-hand rule in this case, you're going to point in the direction of the magnetic flux, which the magnetic flux is, the changing magnetic flux is in this direction. We're increasing, and because it's an increasing magnetic flux, we're going to have a negative current. And so if orthodox current would tell us that it's going counterclockwise, then the actual current is going clockwise, such as true for this case, is clockwise. Okay. So, okay, again, I'll say that again. Point your thumb in the direction of the changing magnetic flux, which in this case we have an increasing magnetic flux. Okay, so we're pointing positively upward. The rest of our fingers wrap around in a counterclockwise direction. We have an increasing magnetic flux, which means we're going to have a negative current, a negative EMF. And so if orthodox direction is to wrap around counterclockwise, and we have a negative current because of our increasing magnetic flux, then our current is going to actually be going clockwise, in opposition to where our orthodox direction would be. Right? So these are just rules. That's what I'm saying, is like, if you don't understand the fundamental laws regarding the physical situation, then you're not going to be able to set up a mathematical problem. You're going to either have wrong signs, or you're just going to have wrong units, things like this. So it's something to, there's fundamentals that need to be understood when looking to find a solution to a problem mathematically. Otherwise you're going to plug in things incorrectly. And so this needs to be known. This needs to be known. It's like similar to never mind, I'm not gonna make that analogy out of not wanting to confuse anybody. So alright, let's continue moving forward. Okay, so we have that. Oh yeah, okay, so let's draw our direction of currents and EMF. So again, here, give me a different color. Let's see. I like that. That works. Right hand rule tells us this way, and it's gonna go opposite direction. Now, if it was a decreasing magnetic flux, then things would go in the orthodox direction, but because it's increasing, we have negative current and EMF. Again, just the way that it is. Laws of the universe, laws of nature. It is the way that it is. And we come up with these fundamentals based off experimentation and based off of what we perceive. A perception that is depicted by nature and by the natural laws, things that have been coded, programmed into the universe by God. Okay, so beautiful. Let's continue on. Okay, so this was pretty much like finished with that section. This was just like understanding the application of Lenz's law. Just understanding the application of Lenz's law. Basically that the induced magnetic field looks to oppose the changing magnetic flux. So again, as I said, we have an increasing magnetic flux, then our induced magnetic field is going to be in the opposite direction. If we had a decreasing magnetic flux, decreasing magnetic flux, then our induced magnetic field would be in the opposite direction. Because you have, with this particular scenario and the things that we're discussing, you have two variables pertaining to the magnetic flux itself. You have its direction, and then you have the direction in which it's changing, whether it's increasing or decreasing, and then its direction being positive or negative. So these are two things you have to account for. The induced magnetic field will be in the desired direction if the induced current flows as shown in figure 29.13. Figure 29.14 shows several applications of Lenz's law to the similar situation of a magnet moving near a conducting loop. I can't read for sure right now. In each case, the induced current produces a magnetic field whose direction opposes the change in flux through the loop due to the magnet's motion. Okay. And so now it's giving you a couple examples here. Let's see. Everything makes sense. Yeah, that way, opposite. Decreasing upward flux through decreasing upward flux. Decreasing upward flux. Decreasing downward flux through. Okay, very interesting. We have some different depictions here of different scenarios where the magnet is either north or south pole facing the loop of wire, moving either towards it or away from it. Increasing downward flux, decreasing upward flux, decreasing downward flux, decreasing upward flux, decreasing downward flux, increasing upward flux. Interesting. The induced magnetic field is upward to oppose the flux change. To produce the induced field, the induced current must be counterclockwise, as seen from above. The induced magnetic field is downward to oppose the flux change. To produce this induced field, the induced current must be clockwise, as seen from above the loop. Okay. Lenz's law and the response to flux changes. I wonder if I should almost draw these out. Since an induced current always opposes any change in magnetic flux through a circuit, how is it possible for the flux to change at all? The answer is that Lenz's law gives only the direction of an induced current. The magnitude of the current depends on the resistance of the circuit. The greater the circuit resistance, the less the induced current that appears to oppose any change in flux, and the easier it is for a flux change to take effect. The greater the circuit resistance, the less the induced current that appears to oppose any change in flux, and the easier it is for a flux change to take effect. If the loop were made out of wood, an insulator, there would be almost no induced current in response to changes in the flux through the loop. Conversely, the less the circuit resistance, the greater the induced current and the more difficult it is to change the flux through the circuit. If the loop in figure 29.14 is a good conductor, an induced current flows as long as the magnet moves relative to the loop. Let me reread that. Figure 29.14 is a good conductor. An induced current flows as long as the magnet moves relative to the loop. Once the magnets and loop are no longer in relative motion, the induced current very quickly decreases to zero because of the non-zero resistance in the loop. The extreme case occurs when the resistance of the circuit is zero. Then the induced current in figure 29.14 will continue to flow even after the induced EMF has disappeared. That is, even after the magnet has stopped moving relative to the loop. Thanks to the persistent current, it turns out that the flux through the loop is exactly the same as it was before the magnet started to move. So the flux through a loop of zero resistance never changes. Exotic materials called superconductors do indeed have zero resistance. We discuss these further in section 29.8. Okay. Alright, section 29.4, emotional electromotive force. Emotional electromotive force. Okay. Yo, what's up, everybody? I hope everybody's having a good day. What's happening? What's happening? What's happening? Oh, let's turn on the music. What's happening? Okay. So that's what we're looking at. Let's move on to emotional electromotive force. We've seen several situations in which a conductor moves in a magnetic field, as in the generation discussed in example 29.3 through 29.6. We can gain additional insight into the origin of the induced EMF in these situations by considering the magnetic forces on mobile charges in the conductor. Figure 29.15 shows the same moving rod that we discussed in example 29.5, separated for the moment from the U-shaped conductor. The magnetic field B is uniform and directed into the page, and we move the rod to the right at a constant velocity v. A charged particle Q in the rod then experiences a magnetic force. Force equals charge times velocity crossed into the magnetic field, with magnitude F equals QVB. We'll assume in the following discussion that Q is positive. In that case, the direction of this force is upward along the rod, from B toward A. Okay. This magnetic force causes the free charges in the rod to move, creating an excess of positive charge at the upper end A and negative charge at the lower end B. This in turn creates an electric field E within the rod, in the direction from A toward B, opposite to the magnetic force. Charge continues to accumulate at the ends of the rod until E becomes large enough for the downward electric force with magnitude QE to cancel exactly the upward magnetic force with magnitude QVB. Then QE equals QVB, and the charges are in equilibrium. The magnitude of the potential difference VAB, VA minus VB is equal to the electric field magnitude E multiplied by the length L of the rod. From the above discussion, E equals VB. With point A at a higher potential than point B. Now suppose the moving rod slides along a stationary U-shaped conductor, forming a complete circuit. No magnetic force acts on the charges in the stationary U-shaped conductor, but the charge that was near points A and B redistributes itself along the stationary conductor, creating an electric field within it. This field establishes a current in the direction shown. The moving rod has become a source of electromotive force. Within it, charge moves from lower to higher potential, and the remainder of the circuit charge moves from higher to lower potential. We call this EMF emotional electromotive force, denoted by epsilon. From the above discussion, the magnitude of this EMF is okay. Alright, I'll draw some shit out so that we can have a visual and get a better understanding for it. Alright, so this is what we have going on here today. This is what we got going on here. Alright, so we're gonna move this over. Give us some fresh page. Yes, sir. Change him back to black. And we're back in black. Okay. Alright, so what we're looking at here. Okay, good enough. Good enough, okay. And then we got our positive. Come on now. Come on now, really? Okay, so velocity. Oh man, my drawings on here just, oh, they're so bad. Oh man, it's really, I don't know, it really grinds my gears, you feel? Just because I want a good drawing and I can't get a good drawing. I go one way and then my line go the other way, you know what I mean? Intel's pad. Okay, there, that's better. Alright, there. Okay, this is our velocity. Fuck, really? Look at my fucking arrows. Alright, whatever, we rolling with it. I'm rolling with it. Okay, there. I don't even look like velocity. Okay, there, that's good. Okay. Velocity. And then we have a magnetic field going into the page. I don't know. This is our magnetic field B going into the page. Yeah. This is everywhere. Magnetic field all over. Magnetic field everywhere. Every inch. Okay. Alright, that's our positive charge. Let's not forget Q. Here, let me, I'll put it here. Positive charge Q. Let me give it a different color. Okay, there. Alright, charge Q. Okay, so this is our charge Q, and then we have, right, this is what charges in the moving rod are acted upon by a magnetic force, and the resulting charge separation creates a canceling electric force. Charges in the moving rod are acted upon by magnetic force, and the resulting charge separation creates a canceling electric force. Yes. Okay, and we have this length of this rod. Oh my goodness. Okay, let me retry. Alright. Alright, so you got that. This our length L. Call it L. Partial stroke. Yes. That's exactly what I want. Oh, beautiful. Alright, so there's that with our length. Again, we denoted B. Alright, and then because of this magnetic field, we're going to have a force acting on this particle right here. Represents just a... I mean, it's just a particle. I don't really understand why represented as a positive charge. But whatever, what does it matter? Right, went like that. Charge. Okay, so velocity. Velocity, electric field, and we got a force this way. Okay, so according to the right-hand rule, if you begin with your fingers pointing in the direction of the velocity. How can I represent this better on screen? Fuck. I don't know, just try it with me. Have all your four fingers pointing in the direction of the velocity and then curving towards the direction of the magnetic field. So pointing in the direction of the velocity, curving, which is going to represent the direction of my magnetic field. My magnetic field is pointing this direction. Curling, so in the direction of the velocity, curling towards the direction of the magnetic field. And the direction that your thumb points is the direction of the magnetic force acting on the particle. So we have velocity in this direction, a magnetic field in that direction, and then we have our thumb pointing upward, which means our force is going to be in that direction. So that's the direction of our force. But I'm going to get rid of that for now because it's not, I don't want that on there. I just want to represent it. Okay, and then, so we got those two things. And now because of, because the right-hand rule is always applicable, but we must understand that when applying this, the results of the application are different based on the charge of our particle. So right here, we're looking at the positive charges. Which can mean just any atom lacking the electron, because in a conducting material, the electrons are free. It's like a free sea of electrons, and where they are able to move around with no limitations. I mean, with inside the conductor, right? And then people say that the charges move along the surfaces and things like this. But anyways, you know, you have this free sea of electrons in conductors. So when we look at a positive particle, let's just consider it an atom of the metal, because the electrons are free to roam. So with this being said, and let's assess the positive particles, we know that the positive particle, the direction of the force will be this way, right? Because of, because of natural law and the way that the physics naturally work, because the program of the universe created by God, that positive charges are going to experience a force in this direction when moving through a magnetic field facing into the page, and under a velocity in this direction perpendicular to the magnetic field. You get this perpendicular force. Okay, and then if we have a negative particle, the right-hand rule still applies, but it's in opposite direction because it's a negative particle. So we're still velocity in that direction, curving into our magnetic field in that direction, and the force is in this direction. But because it's negative and not positive, we just reverse the force, and it's in that direction now, okay? Because of the charge of our particle. When you have positive and negative, you usually have the reverse of one another. But you got to be very particular about what you're talking about, because I guess, I mean, you know, it seems simple to me, but when assessing these problems, you can almost forget what's interior and what's exterior, what values pertain to the object and what values are exterior to the object, such as the object we're assessing right now is the particle. The magnetic field is exterior to this particle, and because of natural law, they happen to interact with each other, although not everything always interacts with each other. You know, just to throw that point out there, the magnetic field and the charged particle do interact with each other. So, it's just important, similar to how important it is to understand the fundamentals of these physical situations, the fundamentals of these physical situations, so that when applying mathematical laws to it, you're not applying the law in a wrong way, right? So it's kind of beautiful, you know. It's like looking at the arts in physics, because it's not all just applying mathematical models and things like this. Although these the things that I am discussing and referring to can be described mathematically simply by signs, right? By the negative and positives, but and like when doing vector mathematics too, negatives and positives are really implying direction, right? Because vectors are values with directions. Whereas a scalar quantity is just simply a value. You know, it has no direction in space. But vectors, they do. And vector mathematics is a whole genre of mathematics, and it's very beautiful. But, yeah. I don't know, and we'll get into more of that too. Right now I'm doing my studies, so I'm studying for myself. And then what I am interested in streaming is the end of the chapter problems, where I'm taking all the knowledge I learned from the chapter and I'm applying them to actual problems. So through that process, I can give you a better understanding of how to assess physical situations. And I'll bring back the fundamentals, and then obviously we're going to be working with the mathematics, working with vectors and calculus, algebra, trigonometry. And so it's going to be beautiful. And sometimes we get into problems that even correlate with chemistry, right? Because physics is like it's just the fundamental of the universe. It's universal law of physics, and so chemistry, it's reliant on the underlying physics, but we describe it as a separate discipline because of how it's just taking its own course. Holy smokes, it's really beautiful though. Art and chemistry too, I love chemistry. But anyways, if we come into a problem where it correlates with chemistry hardcore, but we're studying the physical aspect of it, then maybe we jump over onto a tangent and look into the chemistry of it and explain that a little bit, because chemistry is magical too. Chemistry is very magical. But alright, cool. Cool. How long have we been going for? It's been over an hour now. Alright, good. Let's continue moving forward. Let's finish assessing this section, and then I'm probably gonna log off, to be real with you. But what's up, everybody? I hope you're enjoying the stream. I got like 4 people watching, bro. No, that's lit though, that's lit. I don't know, I think eventually people will, I myself will understand better how to where to take this directive-wise and motive-wise. Like right now I just want to stream. And put up some content, put out some videos, and so that's kind of what I'm doing with it. But I want to become a bit more organized and actually create some sort of curriculum. I don't know, if I'm going to be doing the physics thing, I better create some sort of organized curriculum and present it in an organized fashion with like a theme. Make it entertaining, obviously, because what is education without entertainment? How boring do these concepts become if you don't have somebody on the other end presenting it with inspiration and how we must inspire other people. Sometimes I become uninspired and I don't even know what to do with myself, and I feel like I'm wasting time. I feel lazy and I hate it. I feel like a burden to society, and I feel like I'm sinning in God's presence when I'm being sloth and being lazy. You know, I enjoy being productive and I enjoy progressing in this life, spiritually, physically, mentally, whatever it is, intellectually, Alright. So looking at this problem, let me write down these equations describing the force then. So what's happening here is that so we have a magnetic field here due to the presence of maybe a magnet which has a uniform magnetic field, constant uniform magnetic field. That's just a natural property of magnets due to what is it called? Due to motion of electrons in the conductor's lattice itself. You know, the motion of these electrons are creating all of these electrons in the lattice of the magnetic material are moving in an orbit, all in a similar direction, that they give rise to a net magnetic field in a uniform direction. And so because of the motion of these electrons, these subatomic particles, a magnetic field arises. Whereas in like conductors such as like iron is a ferromagnetic material, but unless it is introduced to an exterior magnetic field which magnetizes it, the electrons for the most part are just moving in random motion in directions that the magnetic fields produced by the motion of the electrons cancel out because of opposing fields, because the motion is random. And if you have like inductors, or not inductors, if you have insulators that are not, how would you say this? I want to make sure I'm saying it correctly and I'm not giving out false information. But if you have an insulator, their electrons don't take on these orbitals. Alright, would you say it that way? Ah, fuck. Alright, forget it. Let's go back to what we're actually discussing. I'm going off on a tangent here, describing what for what reason. Right. Okay, oh yeah, this is why I even began discussing that. Okay, so how does that apply to this? Because I started just get off on a tangent and wasn't even gonna relate it to what we're talking about. Okay, so we discussed that the magnetic force is going to be different depending on whether you have a positive charge or a negative charge. So just understand that, keep that in mind, and don't fucking forget it, okay? Alright, so let me get rid of that, get rid of this. And now, as I said, okay. I want to remember why I was bringing up the magnetization thing. Nah, I can't remember, but anyways, okay. Okay, that didn't work. I don't know. Can I even draw a straight line on here? Is that possible? See, like, what's up with this angle? Because I just drew a straight line, and according to the dots on my influence, like it has an array on it, it has vertical dots and it has horizontal dots. I draw a straight line vertically, and it was at an angle on here. So, what sense does that make? But whatever. All right. That just looks like piss. That looks like I'm gonna get really mad actually. I'm starting to get annoyed as hell. Holy shit, bro. Like, what are these angles? I'm not doing anything different on either side. See, I draw a line. I did one line. I did the other one nearly the exact same. Alright, whatever. Alright, we're gonna go with it was like fucking dog shit. Alright, Alright, we're gonna... Okay, so... Yeah, these are where all the positive particles are gonna go. This is where all the negative particles are gonna go. Well, we're gonna call it B, we're gonna call that A. Okay, so because of the magnetic force acting on the particles, the positive particles are gonna collect at the top of this conductor, and then the negative particles are going to collect at the bottom of the conductor due to the magnetic forces acting on them. And the separation of particles, the separation of charges, is going to create an electric field in between the separated. And the resulting charge separation creates a canceling electric force, right? And this electric field itself will create, or this electric field itself has an electric force. So let's look at this. Okay. Look at the magnetic force. I don't know what's going on. Maybe I won't use this into a passive fucking streaming. Okay. Okay, so the magnetic force equals QB. I'm trying to write without putting my elbow down or resting my hand on the pad. Oh, it's gonna be fun. It's gonna be a trip. Okay, I love how it lags and stuff. Okay, this is what you get when you don't put your hand down and you just write with your shoulder like an artist does. Like an artist is meant to do. Good technique. Okay, there you go. You like it? Does it look good? Does it look really good? Fuck. Fucking get rid of all of it. There. Fucking bitch. Sorry. It's annoying to piss out of me. Okay, Q. Velocity. Magnetic field. Okay, then the electric force. E equals... charge times the electric field. Okay. Okay, and so this magnetic force causes the free charges in the rod to move, creating excess of positive charges at the upper end A and negative charges at the lower end B. This in turn creates an electric field E within the rod, in the direction from A toward B, opposite to the magnetic force. Charge continues to accumulate at the end of the rod until E becomes large enough for the downward electric force with magnitude QE to cancel exactly the upward magnetic force with magnitude QEB. Then QE equals QEB, and the charges are in equilibrium. The magnitude of the potential difference VAB equals VA minus VB is equal to the electric field magnitude E multiplied by the length L of the rod from the above discussion. So it's saying that VAB, the voltage from A to B, equals VA minus VB, obviously VA minus VB, and this is equal to E, the electric field, multiplied, oh yes, by the length of the rod, EL, like that. E equals VB also, the electric field also, because these are equal. Okay, because the magnetic force is equal to the electric force, then E also equals VB. Okay, in this scenario, and so we can say VAB also equals EL equals VL. Velocity times the magnetic field times the length, and the electric field times the length. With point A higher potential than point B, now suppose the moving rod slides along a stationary U-shaped conductor, forming a complete circuit. No magnetic force acts on the charges in the stationary U-shaped conductor, but the charge that was near points A and B redistributed itself along the stationary conductor, creating an electric field within it. This field establishes a current in the direction shown. The moving rod has become a source of electromotive force within it. Charge moves from lower to higher potential, and in the remainder of the circuit, charge moves from higher to lower potential. We call this EMF emotional electromotive force, denoted by epsilon from the above discussion. The magnitude of this EMF is. The magnitude of this EMF is velocity. Like, why is it? Alright, I need to put this down in my notes, my physical notes. It's really neat though, it's really neat how subjecting a conductor to a magnetic field produces an electric field inside the conductor. Wild stuff. The Hall effect, wild. Yo, what's going on? How's everybody doing? We're studying some physics here. Yes, sir. Yes, sir. I don't know. I'm getting focused now. All right. Emotional electromotive force. Oh, okay. We're cooked. We're absolutely cooked. Alright. Okay. Where are we at? Okay, yeah, I do. I gotta draw something similar to this in my notes. I simply have to. This corresponds to a force per unit charge of magnitude velocity times magnetic field. Magnitude VB acting for a distance L along the moving rod. This corresponds to a force per unit charge of magnitude VB acting for a distance L along the moving rod. If the total circuit resistance of the U-shaped conductor in the sliding rod is R, the induced current I in the circuit is given by VBL equals IR. This is the same results we obtained in section 29.2 by using Faraday's law, and indeed motional EMF is a particular case of Faraday's law. Verify that if we express V in meters per second, V in Teslas, and L in meters, then epsilon is in volts. The EMF associated with the moving rod is analogous to that of a battery with its positive terminal at A and its negative terminal at B, although the origins of the two EMFs are quite different. In each case, a non-electrostatic force acts on the charges in the device. In the directions from B to A, and the EMF is the work per unit charge done by this force. And the EMF is the work per unit charge done by this force when a charge moves from B to A in the device. When the device is connected to an external circuit, the direction of the current is from B to A in the device and from A to B in the external circuit. Note that a motional EMF is also present in the isolated moving rod. In the same way that a battery has an EMF even when it's not part of the circuit. Okay, so let me look some up real quick, just to give a depiction of what we're talking about. Emotional, EMF. Emotional EMF, baby. It's kind of like what it was giving us with the whole rod and all. Moving the magnetic field, applied magnetic force, applied magnetic force, velocity, or applied force, emotional EMF, emotional damage, emotional EMF. Alright, cool. I don't know, I'm probably going to continue to study, but I'm going to hop off the stream. I appreciate everybody who tuned in. I don't know, I need to become a bit more organized and think of actual, like, themes for content and things like this, but in due time, I'll get better with it. So, until next time, y'all, take care.